introduction. Hi everyone, I'm Shivram Venkatraman, and today I'm going to be talking to you about some recent work we've been doing on building a low latency execution engine for Apache Spark. This is joint work with Aurojit Panda and Kay Osterhout from the MLLIB at UC Berkeley. Before I get started with my talk, a few words about who I am. I'm a PhD candidate in the MLLIB, advised by Professors Mike Franklin and Jan Stoika. My dissertation is largely focused on designing systems for large-scale machine learning. I've been involved with the Spark project for many years now, and I'm a committer and a PMC member on the Apache Spark project. Most of my contributions are predominantly in Spark core and MLLIB, and more recently I worked on building the R interface for Spark, which is called Spark R. So coming back to today's topic, the main focus or the main thrust behind this work is the growth in the large number of low latency workloads that we see deployed in large scale data centers. So what do I mean by low latency workloads? Let's work with a very specific example, and in this case I'm going to use Spark streaming or a stream processing engine as an example of a low latency workload. So as many of you in this room may know, people have used Spark streaming. One of the key factors in performance is in how quickly can you process the incoming events, or the latency of processing these incoming events. So Spark streaming uses this micro batch model, which has a batch interval that determines this latency. Choosing the right micro batch model is often a question that comes up very often in mailing lists. And it's also something that is being used to benchmark these systems in terms of trying to figure out how fast they can process events. And not only that, because of the related reason that latency is such an important factor, many tutorials, and including this programming guide, contain sections on how you can minimize your latency by setting up your job appropriately. So what are some of the more fundamental challenges that come up when you try to push the latency down below, say, to a sub-second level to orders of let's say hundreds of milliseconds or even lower than that? So the main problem that comes around is with respect to how we evolve our execution model as our latencies for the processing gets lower and lower. So Spark, as many of you know, has this sort of a centralized scheduling model where we have a main driver that sits at the heart of our Spark programs, and that schedules execution of all of our tasks on many machines that may encompass our cluster. So more specifically, we might have a large cluster of machines that we are running on EC2 or some in-house clusters. And what we see is that whenever that data comes in, we form these micro batches that are going to be executed by Spark streaming. Now, each of these micro batches are then submitted to the centralized scheduler, which then places these tasks to be executed on the cluster that it controls. So this is done for each batch that follows one another. And you can see that as we reduce our batch time to, let's say, to be a few milliseconds, and as our cluster sizes grows to, let's say, hundreds or thousands of machines, this centralized scheduling model could lead to significant overheads because of that. So the main focus of this talk is how we can evolve the execution engine that we have in Apache Spark and enable it to get low latency by designing something new. We see that this pattern of a large number of low latency queries that need to be executed comes up in a number of different settings. I've used stream processing as the main motivation in this talk so far, but we also see a similar pattern show up in a large number of machine learning algorithms, and thus we're going to build something general that is able to work with a large number of workloads. So before I get into the details of how we go about doing this, let's talk a little bit of background into the different kinds of parallel execution models that can be used to support these kind of low latency iterative workloads. So to start with, let's use the model that we are most familiar with, which is this batch processing model that's used by systems like Spark. So for example, let's say we are running a streaming word count job. And in each batch of our job, we want to execute two stages. So in the first stage, we want to break up the input stream that we have into a number of different words. So for that, what happens is the centralized driver, it launches a number of tasks on each of the machines that you have. And each task in turn computes the map function that you've written to split the input data. Now, once each of these tasks finish, they send back a notification message to the centralized driver saying that the task is completed and that the output is being recorded at the local machine. Now, when all of these tasks finish, the centralized driver then knows that it's safe to launch the next stage. And this next stage involves the shuffle happening, where data from the previous stage is transferred to these reducers, which then accumulate them to form this sort of word count. Now, once the second stage also finishes, this data, the task send back a notification to the central driver, and this could be the end of, let's say, one iteration of our computing of our batch job. So typically, the next iteration might want to reuse some state that we computed in the previous iteration. So let's say we are broadcasting all of the word counts that we have in order to update them in the next round. And so at the beginning of the next iteration, the centralized driver is also used to share data across iterations and send this data out through a broadcast variable. So in this batch processing model, you might notice a number of salient features that sort of distinguish it from other models. So the first salient feature is that we use centralized task scheduling here, where there's one driver which controls launching and coordinating tasks for all of the stages. And not only is the centralized driver used for task scheduling, we also see that it's used for communicating data between these stages. So we see that in two cases. So for the shuffles, it coordinates the metadata, or rather who should fetch data from whom. And for broadcast variables and things like that, it actually facilitates data sharing by shipping data from the driver to all of the machines that need it. Finally, because of making this particular design choice, we see that we get a lot of benefits in terms of higher level features. For example, Spark implements lineage-based fault recovery, and some of the earlier research work in Spark streaming was in around how we can parallelize recovery and make it faster than other models. This model is pretty popular. It's not only used by Apache Spark, but also by projects like Apache Hadoop and Dryad, which was a Microsoft project. So what's another alternate model for doing this? An alternate model, which is a pretty traditional model and also has been growing in popularity in recent open source projects, is this model that I like to call as parallel operators. So in the parallel operator model, what happens is that at the beginning of execution, there's a centralized driver which sends messages to all of the machines in the cluster and schedules some long-running operators on them. So in our word count example, we would schedule some map tasks on all of the machines once at the beginning, and we'd also schedule some reduced tasks which will accumulate these word counts on the respective machines at the beginning of time. Now when new data arrives, or whenever there's a trigger from externally in the system, these tasks are triggered and they process them per the computation that has been scheduled there. Now because all of these tasks have been pre-scheduled, we can do this shuffle without communicating with any centralized driver, and thus an iteration can execute without any coordination from the centralized driver in this case. So the distinctive characteristic of these long-running these parallel operator design model is that you have these long-lived operators that live on each machine and that execute for a long period of time. And this enables low latency because you can avoid all sorts of coordination that we had in the previous model. However, there are other things which become more difficult here. So for example, to do fault tolerance, you probably need to use some distributed checkpointing algorithms, or even other things let's say, using query re-optimization. So earlier today in the keynote, Michael gave a demo where Spark was automatically re-optimizing the queries for doing code generation or something like that. Those things become very difficult once you have these long-running operators across the system. So it seems like we have two extremes here, and there's some trade-offs associated with this. And the main focus of this work is in trying to see if we can take the Spark model that we have and still get the low latency that we get from the parallel operators. So to give you an idea of some of the challenges that sort of face us, we ran a very simple job, which was just computing the sum of a bunch of random numbers, and we scaled this job from 4 to 128 machines using Apache Spark. So the breakdown here shows how much time the task spends in different parts of the computation. And the red and the orange and the light orange bars are sort of the overheads imposed by the centralized coordination model that we have. That is the scheduler delay and the task fetch. The green colored bars are the ones which are actually doing work, which is the computation and let's say the network transfer. So what we see is that at 4 and 8 machines, our overheads are pretty low and we're spending most of our time doing computation and network weight. But that as we go to 128 machines, these overheads actually start dominating a lot. In fact, at 128 machines, we spend around 150 milliseconds just doing scheduling and fetching our tasks, and this is over 70% of the overall execution time. So this just shows that as our iterations keep getting smaller and as our clusters keep getting larger, these overheads actually form a very significant fraction of the overall execution time. So in this project, we asked this question, can we achieve low latency while keeping this model that Apache Spark has? And we answer this question as yes, using a specific design insight for the kind of workloads that we run. So at the beginning, I mentioned this pattern of like low latency iterations and coordination using like shared state between these iterations. And our main insight is that there are two things which are being considered here together in the existing model that we can sort of break up in order to get the benefits of both the models that I talked about. So on one hand, we want to keep fine-grained execution. That is, we want our streaming jobs or our machine learning jobs to operate on these millisecond granularities. But on the other hand, we find that we actually don't need to do scheduling at the same granularity. So we could do scheduling and fault tolerance at the granularity of, let's say, a few seconds while we're doing execution on the order of, let's say, a few milliseconds. This gives rise to our insight that we can do fine-grained execution with coarse-grained scheduling and thus achieve the benefits of both the models that I described before. So based on this insight, we proposed this like execution engine. We built this and we call this as DRIZZLE. And it contains three main techniques that we use to achieve this. In order to overcome the centralized task scheduling overheads, we propose this technique called batch scheduling. And I'll discuss how it works in this talk. In order to handle shuffle operations that might happen, and in order to remove the centralized coordination of metadata that's happening, we've come up with this technique called pre-scheduling shuffles. And finally, to enable data sharing without, again, going through a centralized driver, we developed this technique of using distributed shared variables. So in this talk, I'll give you a quick overview of all of these techniques and then present some results that we have from using DRIZZLE and also how the user-facing programs will change in order to use this. So let's start with batch scheduling. So to discuss about batch scheduling, what I'm first going to do is give you a quick walkthrough of how the existing Spark scheduling engine works and what are some of the things that it does when you try to schedule a job. So at a very coarse-grained level, this is what the Spark scheduling infrastructure looks like. There's a centralized scheduler which has two sorts of like inputs to it. On the one hand, it maintains some metadata about the hosts that are there in the cluster, the number of free cores and the amount of like free memory and so on and so forth. And on the other hand, there's a thread which is like submitting tasks to the centralized scheduler, and these tasks arrive into a queue. Now, whenever new tasks arrive, the scheduler tries to assign these tasks to the respective machines by using some scheduling algorithms. There's been a lot of recent research in developing new scheduling algorithms, and Spark implements a number of these algorithms to give better locality or to improve the locality of like accessing data, to mitigate stragglers, to do fair sharing, and so on. At the end of these scheduling algorithms, what comes out of this is this mapping of like which task needs to run on which host. And this is the output of the scheduler, and then these tasks are then dispatched by serializing and launching them on the respective hosts. So what we can see here is that there's a number of operations that go on inside the scheduler, and this is basically the main source of like having so much overhead. Is when we have thousands of tasks, it's actually pretty complex operations that are going on there. So what can we do to alleviate this overhead? So the main insight is that because we are running these iterative workloads, we actually find that we can share scheduling decisions across a number of iterations. So for example, in our streaming word count job, if we have 4 mappers and 2 reducers, we need not actually figure out where to run the second batch again, and we can reuse the decisions we made for the first batch. Thus, we actually find that we can amortize most of the time that's being spent in the scheduler across a number of iterations for such workloads. This leads to our simple technique that we call as batch scheduling, where instead of scheduling one batch of execution at a time, we schedule a number of such iterations to be run at the same time. So in the previous model, if we had 4 stages or like 4 of these mini batches in streaming, we would go on them one after another and coordinate at the end of every iteration. Now what we instead do is that we schedule a batch of iterations and we only coordinate at the end of a batch. Thus, if batch size equals 2, our execution looks like that, like the second figure as opposed to the first figure. And the main trade-off that we have achieved here is that Before, we could do scheduling and fault tolerance at the end of like every one of these iterations that we were running. Now we can only do them at the end of every batch of iterations that we run. But if our batch is going to be very low latency, let's say on order of like hundreds of milliseconds, we believe this is a worthwhile trade-off to make where we only coordinate on the order of like a few seconds or so. So how much does batch scheduling help? So to do this, we repeated the same micro benchmark that I showed you before, which is computing the sum of like random numbers. And we ran this with varying batch size. Like we went from 10 to 50 to 100, and we were running 100 iterations overall. So the first bar here is the baseline, which is just Apache Spark 1.6.1 running without any changes. And we see that as we go from 4 to 128 machines, the time taken goes from around like 30 milliseconds to around 300 milliseconds or so. We find that batching helps us significantly reduce this overhead of scheduling and task fetch that we observed before. And that using a batch size of, let's say, 50 brings down the overhead to around like 3 or 4 milliseconds with 4 machines. And even as we go to 128 machines, it's only like 7 or 8 milliseconds that we're spending overall. The benefits sort of diminish as we keep increasing the batch size. And at batch size 100, we sort of see that we can run an iteration in less than 5 milliseconds across like 128 machines. So this result is very exciting because it means that we've driven down this overhead from the order of like hundreds of milliseconds to a single-digit millisecond number, even on a cluster which has like 128 machines and 4 cores per machine. So around 500 tasks that are being running per iteration here. So that was a quick overview of batch scheduling, and now I'm going to switch gears and talk about how we manage data coordination in terms of like pre-scheduling shuffles. So to do that, I'll again present a quick overview of how shuffles work in existing Spark implementation, and then show what are the changes that we need to make in order to remove the centralization aspect of it. So in existing Spark, we have 2 stages. I'm going to call it the map stage and the reduce stage. And the map stage first runs and produces some intermediate data, which is shown in the blue boxes in the figure out there. Following which, the maps task send this status message to the centralized driver saying how many bytes were produced and like where should these bytes be transferred, like to which reducer. Using this metadata, the scheduler then can make decisions on where to launch these reduce tasks and instructs them to fetch the map output from the previous stage, and the tasks then pull the data from wherever they were produced in order to complete the shuffle operation. The 2 key aspects to keep in mind here is that the driver coordinates this metadata management of like how many bytes to fetch from where, and that the tasks pull data from wherever they were produced at the source. Now, in order to remove this centralization of metadata management, we use this technique that we call as pre-scheduling in DRIZZLE. So the main idea behind pre-scheduling is that instead of starting these tasks which are going to receive the data after the first stage complete, we're going to start them before the first stage even starts. So we're going to reverse the order in which we schedule these things. So what we do is we first schedule the reduce tasks here. They're shown in these like gray circles. And they're not active, they're not running, but they're just queued up for running in the future. So what we can then do is that when we launch these map tasks, we can then set up enough metadata information on where these data blocks should be transferred. And thus, once the map tasks finish running, they can directly coordinate with where the reducers are and perform the data transfer. So as you can see, what we've done is that we've removed that red box from within the execution of the 2 stages themselves. And thus, if we can run many more iterations like this, we can go ahead without centralized coordination for like a long period of time. So the last question here is how do we do this like data transfer between the map and the reduce task? And for that, we use this technique where we push metadata and pull data. To give you a quick overview of how this works, whenever these map tasks finish, they still send the same metadata that they were sending in the existing Spark implementation, but now they send it to all of the reducers that are running instead of the centralized driver. And then once the reducers have received metadata messages from all of the map tasks, they then start the pull-based transfer, again similar to the existing Spark implementation. So to show you how well this works, we use the same micro benchmark as before, but instead of running 1 stage for each iteration, we now run 2 stages, a map stage and a reduce stage. And we again vary the number of machines we use from 4 to 128. So what we see is again a result similar to the previous one, where the baseline goes from around like 40 milliseconds to around 330 milliseconds or so, while DRIZZLE scales better. It goes from around like 8 or 9 milliseconds to around 70 milliseconds. You might observe that there's a jump between like the 5 millisecond number that we were talking about before to the 70 millisecond number here. And this is mostly due to the data fetching overhead of opening connections to 128 machines and fetching blocks from there and so on. So that gave you a quick overview of how we deal with shuffle dependencies in DRIZZLE. And the last thing that I'm going to talk about is how we enable data sharing without, again, using a centralized driver. So to do this, we use this idea of distributed shared variables. Now, the idea of distributed shared variables isn't particularly new to our setting, and it's been investigated in many different systems before. If you go back to even using MPI, there are patterns like MPI all reduce that are basically implementing a shared variable where the updates to the shared variables are disseminated across all of the machines. More recently, we've seen people use parameter servers, which are sort of like these shared big model vectors in machine learning that are updated by all of the machines in the cluster. And even a simple reduce followed by a broadcast in Spark is an example of a shared variable because all of the machines update a shared data structure, and then that updates are like broadcast to all of the machines in the cluster. So in DRIZZLE, we specifically build this thing called a replicated shared variable, which is very similar to a broadcast variable, except it's mutable. Tasks can make changes to the broadcast variables. So what happens here is that we have a version number associated with each of these shared variables, and at the beginning of a batch, the version number is set to 1, and all of the tasks get the same data structure similar to a broadcast variable. Now each task performs updates on this shared variable, and these updates are then like collected at the end of a stage and then merged using a custom merge function that can be provided by the user. This generates the second version of the shared variable, which is used for the next iteration and so on. So we've developed some higher level data structures like a dense vector or like a sparse vector, which can use commutative updates, which are commonly found in like these machine learning algorithms. And we are also doing some more research on these merge strategies. So we can probably use like a clever merge strategy of you doing butterfly mixing that will reduce the amount of latency for this merge operations. To give you the other main thing that I'm very excited about for shared variables is that they actually enable asynchrony even within a synchronous system like Spark. For those of you who heard Jeff Dean and Andrew Ng talk earlier in the keynotes, asynchronous updates to these parameter servers has like been a major trend in large-scale machine learning over the past few years. And what these shared variables do is that they enable us to bring in asynchrony within a batch of iterations that are running at a time. So within a single machine, our workflow looks something like a synchronous model where we wait for the merge at the end of every update, or an asynchronous model where we could be using some stale version of the data while the merges are happening in parallel. So we're doing some more research in trying to figure out how much does asynchrony help for some of the machine learning algorithms that are already a part of Spark. So I briefly talked about some of the micro benchmarks that we did before. We've built DRIZZLE on top of Spark 1.6.1, and we have integrations with Spark Streaming and MLLIB. And we've used them to sort of do some streaming benchmarks and logistic regression benchmarks. I'll give you a quick overview of how to use the DRIZZLE API or how it affects users, and then present some end-to-end results. So in terms of the DRIZZLE API, there's a very simple internal API change at the scheduler level that probably doesn't affect any of the users, but the API change goes from being able to run a single job to being able to run a batch of jobs. So we take, instead of a single RDD, a seek of RDDs. But this is this is something that most users will probably not have to touch. Instead, what most users will see is like a more higher level thing, like for example with Spark Streaming, where when we create a streaming context, we pass in an additional parameter of the number of like RDDs to use per batch of the DRIZZLE batch scheduling that I talked about before. And the rest of the complexity gets hidden inside the streaming code, and so it should be pretty easy for users to use. In terms of like choosing an appropriate batch size, we know that the two extremes of the batch size, like setting the batch size to 1 or setting the batch size to n, results in the two models that I talked about before, one being like the batch processing model and n being the parallel operators model. And in practice, what we usually find is that we pick the largest batch size such that our, each batch takes around like a few seconds or so of execution, such that the scheduling overhead becomes very small. And we are working on techniques to automate this so that users don't have to like actually pick this by hand. To give you a quick sense of evaluation, this is still a pretty young project, so we're still doing a lot more evaluation with respect to this. We use this Yahoo streaming benchmark which does like add analytics on like on a batch of data that keeps arriving, and we compared DRIZZLE to like Spark streaming, and the results of that are shown in this graph. So what we found was that in Spark streaming, we couldn't set the microbatch latency to be less than around 500 milliseconds, and that it would get unstable if you made it smaller than that. With DRIZZLE, we see that we're able to set it to much smaller, to around like 90 milliseconds, and that gives us this 5 to 6x win across the CDF of like each of the events that are finishing in this benchmark. We see similar results with the logistic regression benchmark. This is on a small data set, RCV1, but it's representative of how the shared variables and like batch scheduling can give you a pretty big win in terms of like running time per iteration. There's a bunch of other work in progress, like I said, with respect to automatic batch size tuning and more experiments and so on. But we also want to make an open source release and discuss whether this can become a part of the Apache Spark project through the Jira and discuss potential contributions that can be made from this work. So in summary, today, what we saw is that, that there are some significant overheads that come in when we try to run really low latency iterative workloads on large clusters using Apache Spark. To address this, we discussed how we can build a low latency execution engine that decouples the execution granularity from the scheduling granularity, and thus can enable like millisecond level latency for iterative workloads. We're very interested in knowing if there are some workloads that you have that will fit this model well, or if you have any questions or interested in like contributing to our work as well. And you can definitely send me an email, and I'd be happy to talk more after the talk as well. With that, I'll take any questions. Thank you.
Hi, this is very interesting. Are any of the optimizations you described generally applicable to Spark jobs in general?
So it depends. So some of the insights, so for example, like the pre-scheduling that I described can actually be used for any Spark job. So we've even seen that if you have, let's say, a very deep pipeline with like 7 or 8 stages, doing this kind of pre-scheduling can give you benefits across that. But some of the centralized task scheduling things, it's hard to do it for a general purpose Spark job because you still need to schedule those 1,000 tasks, and that's going to take order of like, let's say, 100 milliseconds. And so there are some probably improvements. So along the way, we found there are some improvements we can make to the single node scheduler as well. And so those will apply. But some of the huge wins that we see to, let's say, a 5 millisecond granularity are hard to apply for general Spark jobs. Yeah. There's a question there.
Hi. Yeah, we are using extremely low latency Spark streaming, and I think the version that we are using is on 1.5 or 1.6, and some of the solutions that you described is sitting on top of 1.6.
Yeah.
Right. So are there any techniques below 1.6 that we can use to speed the things up? Yeah. So just to clarify, these techniques are not in 1.6. This is like techniques we built on top of like a fork of 1.6. I mean, to answer your question of whether are there any techniques, I think there are two main things that I would look for in terms of low latency. So one is a breakdown between processing time and like the scheduling time. I think the UI probably has something for it, or like there are other metrics that are being reported for it. And from a user's perspective, I would basically drive down the processing time as a first cut. And some of the processing time improvements, for example, like in the keynote today, we saw the code generation is a very useful way to improve processing time. Or changing the number of partitions or tuning the number of partitions could reduce the processing time. So those would be some of the things that I would look at, even irrespective of these scheduling techniques. One there. Oh, go ahead.
I got a question. So you described the problems with the existing Spark and the problems of scheduling and the synchronicity between the stages. In 2.0, your code, is it going to go and it's going to become part of Spark? do you have the plans for that?
So it's most definitely not going to be 2.0 because 2.0 is pretty close to a release, while this is still this has been under more recent development. But we do want to discuss contributing back to Spark in, like, let's say a future version like 2.1 or something like that. And also there's some new streaming frontends, like we heard about the structured streaming API this morning. And so we also want to investigate how we can probably integrate that with this pretty well. But this is a discussion that we need to have with, like, the other Spark committers and, like, other parts of the community as well on the Apache project. But we do hope to integrate this with the mainline project. Yes.
Another question is the checkpointing, right? So basically Flink, they have to do the checkpoints, but the beauty of those checkpoints, they're synchronous, right? So they don't hold on the pipe. So in here, you know, you're talking about shared variables, but I'm just more wondering about actually, you know, what happens is that, you know, you're about to finish the batch, you know, the reducers are all finished, they need to dump the data somewhere. Right. And, you know, did you do any work to actually somehow, like, overlap the batches, you know, so that feature of Flink is actually going to spill into...
That's a good question. So we do some work in that. So what we do is, like, for example, before the first batch finishes, we start forming the tasks for the second batch. So let's say around 50 milliseconds or so before the previous one finishes, we start forming the tasks and doing some of the prep work for the next batch. But there's still, I guess, some more work we need to do on that. I haven't completely profiled it very well. Yeah. All right, one last question probably. I can talk to you after the talk as well. Yeah, yeah.
Sorry. Yes. My question's related to the previous question. I was wondering if you've looked at using sliding window, a sliding window algorithm instead on the input end?
Yeah, so that's a good point. So what we're doing is what we're doing looks like a sliding window where we're taking a bunch of these small windows and calling them as a bigger window. So I think this sliding window applies at two levels. So one is the logical level where the query has a sliding window, and that sort of we are agnostic towards that because we are at the execution level out here. But for example, this batch size tuning where we increase and decrease the batch size, it would be a little bit like changing the sliding window that we are going to use as we keep running the jobs. Yeah. Okay. I'll take any more questions offline. Yeah. Thank you very much.